FAIZAL bin AZHAR. My name is ZULHISYAM. Today we would like to present our first PBL assignment and entitled Power Factor Correction.
Okay, this is task 1 that given to us. A network consists of 3 loads are connected at 3 different nodes as shown in figure 1, and the 3 distribution lines are connected between the main supply and loads. Voltage required by load 3 is 240 angle by 12 degree voltage RMS, and the details of the network are given in table 1. This table shows all the information given for the load across the distribution line. Load 1 have 10 kW power and a lagging power factor of 0.92. Load 2 have 15 kW power and a leading power factor of 0.82. Lastly, Load 3 have 20 kW power and 12 kVAR reactive power. Below shows the impedance of the transmission line per kilometer. Since we were in group 3, we use 3 km of transmission line. Therefore, we need to calculate the transmission line by multiplying the impedance given with 3 km. We redraw the circuit like this to make it easier to understand. Z1, Z2 and Z3 are load 1, load 2 and load 3 respectively. Then, the impedance at line 1 to line 2 is labelled as Z4, while impedance at line 2 to line 3 is labelled as Z5. Lastly, impedance at line 3 to line 4 is labelled as Z6. This is what we get when we calculate the given transmission line impedance by multiplying with the 3 km. The first question given is to find the impedance for each load and the equivalent impedance. First of all, we can find load 3 by using the equation of complex power equal to the square voltage at line 3 divided by the conjugate of Z3. But before that, we need to find the complex power at line 3. To find the complex power, we need to add the real power with the reactive power, which we get 23.32 kilo angle of 30.96 degree VA. Thus, we substitute the complex power into the equation and get the load 3, which is 2.47 angle of 30.96 ohm. In order to find the load 2, we need to know the voltage line at load 2 by using the total impedance at line 3 and current at line 3. Using Ohm's law, we calculate the current at line 3. Then, sum up the Z3 and Z6 to find the impedance at line 3. After that, we can calculate the voltage at line 2. By using the power factor given for load 2, we can find the complex power at line 2, which we get 17.647 K with the angle of negative 51.79 degree VA. The negative angle is given by the leading power factor. Then, substitute the value of voltage line 2 that we get earlier and this complex power into the complex power equation. After that, we will get the Z2, which is our load 2, 3.617 angle negative 31.79 degree ohm. The angle for load 2 we can get from the cos theta given. Then we proceed to find the ZP that we draw in this circuit. To find that, we need to parallel the Z at line 3 and load 2. After that, we can get the current at line 2 by using the Ohm's law. The current is given by 141.96 angle of 7.552 degree ampere. Then we get the ZL2 by adding up the ZP and the Z5 and the Z5 given. Our ZL2 is 1.9 angle of 11.683 degree ohm. So that we can use this information to find the voltage at line 1. Using Ohm's law, the current of L2 times the impedance of L2, we can get the voltage at line 1, which is 269.211 angle of 19.235. We can use that voltage to find this load 1 by using the power given. We can find the complex power of line 1. The complex power calculated is 10.87 kilo, angle of 23.074 degree VA. Then using the same equation, substitute the complex power and the voltage at line 1 we calculated earlier. Then we will get our Z1, which is our load 1, 6.667 angle of 23.07 degree ohm. Lastly, we can get ZP by parallel the Z at line 2 and Z1, which our ZP is this is our new ZP, which is 1.484 at angle of 14.20 degree ohm. Then we calculate the Z total, which is Z4 plus ZP2. Then we get the answer 1.683 angle of 22.14 degree ohm. Okay, the next question given is we need to calculate the main supply voltage, which is IT. When we calculated the voltage at line 1 earlier, we divide it by the ZP2 and the answer is 181.41 degree of 5.035 degree ampere. Then we use that current total times the total resistance. The answer should be 305.31 angle of 27.175 degree volt. Okay, the next question is the current flow in each load and total current supplied by the source. First, we calculate the current total, which is using the voltage at line 1 divided by the total impedance. This we get the 181.41 angle 5.035 degree ampere. Then you can calculate the current at line 3 by using the voltage at line 3 we calculated earlier divided by the load 3, which we get 97.17 angle of negative 18.96 degree ampere. And at current at line 2, we use voltage at line 2 divided by the load 2, which we get 69.85 angle of 45.94 degree ampere. Lastly, we can get the current at line 1 by using voltage at line 1 divided by the load 1. Thus we get 40.38 angle of negative 3.835 degree ampere.
For our assignment, we also need to find the value of real and reactive power losses at the transmission line. At line 1, 2, to find the real power, we use the formula P1 equal to IT square times resistor. The value for IT is 181.41 square times with the value of resistor, which is 0.12, and we get 3.949 kilowatt. For reactive power, we use this formula, which is IT square times with the value of either capacitor or inductance, and this is the value 181.41 square times with 0.27, so we get 8.886 kilo imaginary VAR. Then after we get these two value, we insert it inside the apparent power, which is 3.649k kilo plus 8.886 kilo imaginary VAA, and it's equal to 9.723 kilo, angle 66.04. Next, for the line 2-3, use the same formula like line 1-2, but different value of I and R. For the value of I, we use 69.85 square. We multiply it with the value of resistor, which is 0.09, and it equal to 439.11 watt. For true power, use the same value of the current, then we multiply it with imaginary value. For this line, the value is 0.18, then we get 878.22 I var. And then for the apparent power, this is the value, which is 439.11 plus 878.22 I VA. And this is the value 1.317k, angle 0.957. For line 3-4, the value of current is 97.17 square, and then we multiply it with 0.06, and we get 566.52 watt. For reactive power, the value of imaginary is 0.15, and then we multiply it with the square of 97.17, and we get 1.416 kilo I var. And then this is the value for apparent power, 1.525 kilo, angle 68.19 VA. Next, for this assignment, we also need to find total apparent power, real power, and reactive power for the system. In order to find the total of apparent power, we need to multiply voltage supply with the I total. So this is the value for voltage supply, then we multiply it with the value of IT, then we get this one. Then we change it to the phasor form, which is 55.386 kilo, angle to 2.14. And then this one is the value of the true power, 55.302 kilowatt, and this one is the value of reactive power. These two value we get from the imaginary form from apparent power, and then we form the triangle, power triangle. This one is angle from this form 22.14. This one is lagging because when we use cos 22.14, then we get this value. Then this is the task 2. Based on the work that you design in task 1, design the power factor correction system that helps to improve the system power factor to 0.98. So we use the old value of power factor, and then this one we get the new angle, which is 11.48. Then we use this formula, tan 11.48 equal to reactive nu over 55.302K. This is our true power. Then we get the value for Q, and then in order to find the value of QC, so we minus Q new with the Q old. So this is the value. After that, we get the value for QC, then we insert it into this formula, and then we will get this one, negative 9.6668I. So this one is negative, which is the value of capacitor. And then you insert it inside this one, XC, then you get 0.329 millifarad. So this is the new power triangle for our assignment.
Task 3 required us to use multisim to perform an AC power analysis using the network that already designed in task 1 and evaluate whether the values that you obtain in task 2 are correct. So basically, this is the circuit diagram for task 1 that we already designed, which consists of resistor, inductors, and also capacitor. So first of all, I want to show how to perform the single frequency AC analysis in multisim. So this is the circuit that we already designed for task 1. To perform the single frequency AC analysis, we just click here, and then it will appear the menu like this. First, we need to select the complex number format. In here, it consists of real or imaginary, and magnitude and phase angle. So we can choose whether we want to use either one. So for now, I want to use the magnitude and phase angle. So next, we need to select the output that we want to see the outcome. So here we can see all the variables that are available in the circuit that we already labeled before. So for example, we want to see the current for at load 1, so we need to add. Next, current at load 2, current at load 3. Okay, after we already select and add the current, we need to click save and select the green button here, which is run. So in here we can see the output for current at load 1, load 2 and load 3. In this assignment we use frequency which is 50 Hz, so it will appear the output for current in magnitude and phase as we selected before for current at load 1, 2 and 3 like this. So back to the slide earlier. So here we already screenshot the reading current for each load in task 1, which is I at load 1, load 2 and also load 3. You can see the we choose to see the output in magnitude and phase angle. So next, the circuit earlier we modified a little bit to add a capacitor and also switch. This is because we want to do the power factor correction. So this is the circuit before the power factor correction. We can see here the switch is switch off, and here we connect the wattmeter in order to see the power factor and also the real power. So here is the reading of power factor for task 2 when switch is off, which is before the power factor correction. So we use wattmeter in multisim, and this is the real power, 51.053 kilowatt, and this is the power factor before power factor correction, which is 0.92416. Next, we need to connect the circuit, the switch. We can see here it is connected. So we can see the simulation. We still get the same real power, which is the correct one, 51.053 kilowatt, and the power factor is already become 0.97945. This is because previously we already add the capacitor, that's why the power factor becomes 0.97945. So lastly, we can conclude all the power factor correction in one triangle, which is called power triangle. So as we can see here, the black triangle is the result before power factor correction. We can see here the theta is 22.14, the real power 51.302 kilowatt, the reactive power is 20.873 kJ var, and the apparent power is 55.386 K angle 22.14 volt ampere. So this is the power triangle before power factor correction, and after we did power factor correction, this is the power triangle with the red color. You can see the angle becomes smaller, which is 11.48 degree, and power is still the same, and the value for reactive power is already become smaller, which is 11.231 kJ var. This is because we already add the capacitor parallel to the voltage source, which in result the reactive power become smaller, and also the angle for the power triangle after power factor correction becomes smaller. That's all from us, group 3. Thank you very much.